Hello all, welcome to the oral talk on nuclear transmutations, better facilitated by alloys over pure metal cathodes in electrolysis. The work is done by Ankit Kumar, Raj Pala, Pankaj Jain and KP Rajiv. Introduction first. Electrolysis has become one of the popular low energy mechanism to observe nuclear reaction on electrodes involved in it. Hence, the knowledge on the behavior results of combinations of cathode, anode and electrolyte used is of special interest to the community now. Motivated with this novel phenomena, we perform experiments to induce transmutation reactions through electrolysis of various metals and alloys in deionized water. With carbon as our choice for anode in all our experiments, we do observe transmutations on pure metals like nickel and copper. We also perform experiments on the alloys like nickel iron and Kanthal. Besides transmutations, the results also indicate that alloys undergo transmutations faster as compared to the pure metals. This slide shows the major steps involved in the experiment. First, we choose a pure metal or alloy of our interest and perform its elemental analysis using various material characterization techniques. Secondly, we electrolyze deionized water with the metal or alloy as cathode in potassium carbonate aqueous electrolyte. Finally, we again perform the elemental analysis of the electrolyzed metal or cathode and look for any changes in metallic or isotopic concentration of the cathode caused due to electrolysis. Basically, we compare the result of the first and the last steps shown in this slide to track the nuclear reaction occurring on our samples. Figure 1 on left hand side shows the schematic of the experimental setup. On the right hand side, we have the real picture of the electrolytic cell. We can also see the gas evolved at the electrodes. Now, let us talk about the choice of the electrodes and electrolyte. For the anode, we use high quality graphite, which is 99.99% pure by WDS in all of our experiments instead of noble metals like platinum or so. This is done to rule out the dissolution of anodic metal ions into the solution, thereby leading to electrodeposition on our working cathode, which we don't want. A high quality graphite, which is naturally obtained, is a must for reproducing the results, as a normal graphite rod may be a mixture of clay, graphite and various other polymers and hence disintegrate soon in the solution during the electrolysis process. For the cathode, we focus mainly on pure nickel in most of our experiments, as it is corrosion resistant and is available in standard shape and sizes. Besides nickel, we also study pure copper and alloy like nickel iron and Kanthal. For electrolyte, we use 1 molar potassium carbonate, which is 99.995% pure by trace metal analysis in double deionized water in all of our experiments. The pH of electrolyte is kept neutral throughout the electrolysis. Potassium carbonate shows maximum solubility at a temperature range of 30 to 40 degrees Celsius. The electrolysis is run at 35 degrees Celsius and at normal atmospheric pressure. The bias on the electrodes is in range of 20 to 30 volts imposed via a 2 electrode setup. The power supply provides 1 to 4 ampere current in the circuit and the experiment is run throughout the pre-decided time range. A dry silicon carbide cutoff wheel is used to separate the dipped electrolyzed part of the cathode from the cathode part, which is suspended in the air. We use various material characterization techniques to analyze our samples. Wavelength dispersive spectroscopy (WDS) and energy dispersive spectroscopy or EDS are the primary X-ray spectroscopy technique which we employ to analyze the sample surface. Besides that, we also use time of flight secondary ion mass spectrometry or TOF SIMS to detect all the chemical elements on the surface, and the isotopic analysis along with its depth profile. The machines that we use are mentioned in this slide. So let us start looking at some of our experimental results. We have chosen pure nickel as our metal of interest. Figure 3 shows the EDS of the pure nickel. On the x-axis, we have 4 spots chosen on the sample. So these are basically the 4 different locations on our pure sample, and on the y-axis we have the corresponding mass percentage of those spots. We can see that the EDS says that all the 4 spots had 100% nickel. Now this pure nickel was taken for electrolysis. The electrolysis was done in 1 molar potassium carbonate electrolyte at 30 volts, 2.5 ampere currents, and the time duration was 11 hours. After the electrolysis, the sample shows a lot of transmutations. So figure 4 shows the EDS of electrolyzed nickel. We can clearly see that nickel has largely transmuted to copper 20%, magnesium generated about 3%, and iron, which is present in about 4%. Please note that all of these elements were not present in the initial sample. Hence, we can say that the nickel in the original sample has transmuted to various other elements. We will see the WDS analysis of the same sample in the next slide. In this slide, we show the WDS analysis of the pure nickel sample which was discussed in the previous slide. Figure 5 on the left hand side shows the WDS data of the pure nickel, and figure 6 on the right hand side shows the WS data of the electrolyzed nickel. Again, on comparing figure 5 and figure 6, we find that copper and magnesium has been produced in significant amounts. So copper is present in about 6% and magnesium has been generated at all the 4 spots about 7%. These are quite significant amounts, and the WDS data also confirms the EDS data. Please note that the energy resolution of the EDS is about 100 electron volt, whereas the energy resolution of the WDS is much finer. It is 10 electron volts. Now let us look at another pure metal. Here we have chosen a pure copper metal. Figure 7 on the left hand side shows the EDS of the pure copper. The EDS analysis shows that at all the 5 locations we have 100% copper. This copper has been then taken for the electrolysis in 1 molar potassium carbonate electrolyte at 30 volts, 3.5 ampere current, and the run duration 12 hours. Figure 8 on the right hand side shows the EDS of the electrolyzed copper. Again, we can see that iron and magnesium have been generated in large mass ratio. We can see that on spot 1 the iron is about 4%, at spot 3 the iron is about 8%, at spot 5 also the iron is about 8%. Magnesium has been also generated at all the 5 spots from 1 to 2%. Hence, we can say that copper has been transmuted to iron and magnesium mostly. Let us now have a look at the effects of electrolysis on alloys. In this slide, we start with the Kanthal metal. The Kanthal metal comprises of iron 74%, chromium 22%, and aluminium 4%. On the left hand side, we shows in the figure 9 the EDS of pure Kanthal. We can clearly see that the EDS analysis closely follows the standard composition of Kanthal at all the 5 spots. This pure Kanthal is next taken for electrolysis. The electrolysis is done in 1 molar potassium carbonate electrolyte. Potential bias 30 volts and current in the circuit is 3.5 amperes, and the electrolysis is run only for 1 hour. Figure 10 on the right hand side shows the EDS of electrolyzed Kanthal. It shows that copper has been produced from 20 to 53% and magnesium has been generated about 6 to 11 mass percentage in just 1 hour of electrolysis reaction. This slide shows the WDS data of a nickel iron alloy. Please note that this sample has been electrolyzed only for 1 hour. Looking at figure 11, the WDS confirms the composition of the nickel iron alloy. The nickel is 93% and the iron is 7%. Figure 12 shows the electrolyzed nickel iron alloy composition. We find the generation of copper, which is about 1.8 mass percentage, and the generation of magnesium, which is 6 mass percentage, which was not present in the original sample. Also, please note once again that these transmutations have been observed within 1 hour of electrolysis. Hence, this is also an example of rapid transmutation in alloys. This slide shows the TOF SIMS mass spectrometry data, in which we show a depth profile of the nickel cathode, which has been electrolyzed for 10 hours. The depth profile clearly shows a significant amount of transmutations of nickel to magnesium, iron, chromium and copper. We also see a gradual decrease in the transmutation products as we go deeper inside the sample from the surface. SIMS also records counts of platinum and gold on our samples. This data is in full support of the EDS and WDS analysis, which shows that nickel largely transmuted to copper and magnesium. At last, let us have a look at the isotopic shifts of copper which was produced on the electrolyzed nickel sample. Copper has 2 major isotopes, copper 63 and copper 65. Figure 14 compares these isotopic abundances at 3 different locations on the electrolyte sample with that of the natural abundance. At all the 3 locations, we can see that the abundance of copper 65 has reduced and that of copper 63 has increased. The ratio of copper 63 to copper 65 observed on electrolyte samples are quite different from the natural ratios. This data once again confirms the occurrence of nuclear reactions on our samples. These are the important experimental observations based on the data that we have seen earlier. Number 1. The experimental data discussed in the paper confirms elemental transmutation in metals after electrolysis in deionized water. Please note that we are using H2O and not D2O. Pure metals like nickel, copper and alloys like nickel iron and Kanthal have shown significant amount of transmutations to copper, iron and magnesium, etc. The experimental data have also shown that alloy forms a better choice than pure elements to induce transmutations because of the possible increased number of pathways leading to more hydrogen enabled reactions in less time. At last, we have also seen the TOF SIMS data which confirms the EDS and WDS results. The depth profile also shows that the transmutations has occurred up to a depth of 350 nanometers in our samples. We have also observed the isotopic shifts in copper which was produced on the nickel sample. All this experimental data and observation forms an undeniable proof that metal undergo transmutation even under electrolysis in normal water, and these can be observed within few minutes of electrolysis also. Thank you all. We invite questions.